Hello everybody and welcome to Handmade Hero Show, where I code a complete game live on stream. You may be asking yourself, Casey, what are you drinking today? Hmm? And the answer is, I'm actually drinking handmade coffee. The very first coffee to be officially sanctioned by the Handmade Hero television show. Where can you get some of this handmade coffee, you may ask? Well, I guess the answer is I don't know. It was actually given to me by a viewer of the show at Handmade Seattle. His name is Irad. I don't actually know if he would actually ever take a coffee order for somebody because he hand roasts his own coffee. I think because he is in the Bay Area and said that he thinks the coffee there is not very good. But I posted on Twitter a little shot of the Handmade Hero coffee, and a lot of people were interested to know about it. That is where it came from. I do not make my own coffee. I mean, I get beans, I grind them, and I put them through an espresso machine. That is about as handmade as my coffee gets. But I was extremely honored to be presented with a bag of handmade coffee. And I do think I have actually the Twitter handle for the fellow who made it. It's and I will try to tweet that out. It's at Eradicator, IRADICATOR. So that is where the coffee came from. And if you're interested in handmade coffee, you can hit up Eradicator on Twitter and see if he has any tips for you. I don't even know how he's doing it. I guess he must have some kind of a home roasting setup, which I didn't even know. Do they make like a little roasting thing? I mean, I think if you're in the Bay Area, you can't have a house, can you? You would have to be like extremely wealthy. I don't know. Maybe he is, but just seems unlikely, right? That you'd have like a big outdoor roaster there or something like that. Anyway, thanks again to Rod for that. It's awesome. Yeah, unfortunately I'm running out. So we'll have to be back to the regular coffee probably next week. But until then, I'm on the handmade coffee and it's pretty delicious. This was from Ethiopia beans, Ethiopian beans. You can see it's labeled on the bottom. All right, let's go ahead and get this going. I'm going to switch over Sorry, the new setup. I gotta still getting used to things. So where did we leave off? We've been since we had I was away for one weekend, and then Handmade Seattle was last weekend. So I haven't really been streaming for a while. So you may have forgotten. I mean, I may have forgotten what we were doing. So what are we doing? Well, actually, surprisingly, I didn't forget what we were doing. We were in the middle of doing some work with the raycasting that we use for lighting. And if I go ahead and do a quick build of the game here, and then launch Remedy BG, and you can see a run of the current state of things. What we had just done at the end of last stream, if I'm not in error, is thrown in the Raycaster and had it basically set the lighting in an area based on, to either the correct radial fall off, the radial test fall off, or 0 if the ray to the light source was occluded. And we got this weird modeling pattern, which was a little surprising at first, but then I realized it may not really be all that surprising. And the reason for that is because we were just raycasting from the center, excuse me, we were just raycasting from the center of the voxels, of the lighting voxels. And so it's not particularly surprising that we would get this pattern, actually, now that I think about it, because since we have unevenly, the height of our things is kind of variant, if the centers of the voxels, the places we were casting from, happen to be like sort of along the bottom here, what you would get is you would definitely get this sort of same occluding or non-occluding behavior of the light source as you moved around. Or other things like that could easily happen, right? Depending on whether or not you could see whether or not the particular ray that was cast to that voxel center from the light source hit something or didn't hit something, right? So we actually don't really know. I mean, although, you know, it probably is also, there's some bugs in there because we haven't really done much with that raycasting stuff. But although we don't really know if there's a bug or not, we just know there might be. We aren't really doing what we would want to do anyway. Because what we'd like to do is move, and we're probably going to start this today. I didn't want to start it at the end of last stream because it's a bunch of work, obviously, and we're kind of moving more towards the full lighting solution. But now today we can start down that road. What we want to do is use the positioning of these light probes because that's the whole point of the light probes, right? The idea behind the light probes is that when we build the level, what we want to do is specifically tell the game, here is where we want you to compute the lighting from. Because otherwise we're always going to have crazy artifacts that have to do with the fact that where we choose to do casting from happens to be like inside something, right? So if we actually use the lighting voxel centers, we would be in a lot of trouble because we would constantly be getting artifacts similar to these. So even if there isn't, or I should say, even if what we're seeing right now is just bugs that we're going to go clean up in the actual raycasting or whatever, right? We do also need to address this other potential source of problems, which is the fact that the precise nature of these lighting probes is that we need them to help us not have weird placement of raycasting information. And that's something that we have not done yet. So we need to do both of those things. Both figure out if we've got other bugs that are in the Raycaster. This is the first time we've turned it on since we did all the rewriting. So we have to fix the Raycaster, any bugs in there. And then we need to also, or maybe we do this in the opposite order, we need to be casting and thinking about the lighting from the light probes because that's the whole reason they're there now. They no longer will even be storing any information, which is kind of cool. They're just there. In fact, we could even say they're effectively guides. They're like sampling guides. They're just telling the system where to sample from. They're not even really storing any lighting information anymore, which is great if it turns out we can get away with that. That's actually really fantastic for a number of reasons I've explained before, but basically it means we don't have to track these things through the frame process. Like, we don't have to go from frame to frame knowing that this probe and this probe are like the same probe or anything like that, because all we're doing is just throwing sample points into a system. So every frame we can just throw them in, and then the next frame we can throw in a totally different set if we wanted to, and this would not affect our ability to execute the algorithm faithfully. That's like really great, right? So that's a pretty that would be a pretty big deal, right? So anyway, that's where we're at currently. And so we're going to have to sort of go through this slowly because we haven't been programming in 2 weeks, 3 weeks. And so we kind of got to get back in the swing of things here. If you remember correctly, we're calling build spatial partition for lighting. Build spatial partition for lighting is the thing which basically says, okay, make some acceleration structure we can use for faster raycasting. We probably need to do some work on that, but that's what's going on there. And then compute lighting propagation, as you can see, is turned off. That's because we haven't really gotten to the part where we want to do secondary bounces. That's what compute light propagation will be for, is for like basically doing secondary bounces. So what we're doing right now is we're doing testing, and if you remember correctly, what we can do here is we have some pound defines. Those pound defines determine what kind of lighting test we're running. If I turn to a sphere-based lighting test, what you can see is that we just get the nice radial fall-off version, right? And you can see this has like 4 separate lighting spheres, because we actually allow 4 separate interpolator patterns. That doesn't mean 4 light sources. You can use an infinite number of light sources. It just means there's 4 perfect interpolators in there. And so we just have to output our lighting in a way that 4 perfect interpolators could reconstruct, right? So it's the same as sort of saying, yeah, like if we were playing, say, a series of sound effects, let's say, right? The good way to think about this is stereo sound, right? We all know that stereo sound is sufficient for playing sound to a spatial sound to a certain degree. what it does is it takes all the sounds and it mixes them down so that you put some on the left channel, some on the right channel, and some in both. I mean, most of them go out in both at different ratios. And that mix down is basically taking the actual locations of things, trying to roughly figure out what they would sound like to the left and right ear, and then putting them out through those channels, right? So effectively, you've got tons of sounds. Each one has a particular spatial location, and you're trying to mix down that full set of information into just 2 output sounds that will capture what it should roughly sound like, right? And that's exactly the kind of thing we're doing here. We're saying, look, our output channel is 4 perfect things. So if we only had 4 light sources, you could capture them exactly correctly with the interpolator. But we will probably have more than 4 light sources in some areas, or maybe in all areas. There'll be a lot more. And in fact, really, another way to think about it would be, not only do we have 4 light sources, but there's all the bounces, right? So it's it's like a complete radiosity solution that we're kind of going to have here. And so, what we're trying to do is figure out what that total lighting solution, how do we best present it to the user using only 4 playback channels, is a good way to think about it, right? So we're effectively trying to say, how do we reconstruct as closely as possible the lighting solution we want from that limited number of interpolation parameters that we have, right? But I'm optimistic we'll be able to do it pretty good, right? Because, you can see that it's a pretty good interpolation. It reconstructs things pretty nicely. So I think we should be able to figure out ways to make it work, hopefully. All right. So that's what we're working with. And so what we need to do now is start getting the actual lighting transfer working. And what I did first is, you can see in this transfer test I did here, what you can see is what we're doing here is saying, look, we've got these voxel cells of our lighting solution. What we're going to do is go ahead and pack the voxel cells of the lighting solution and send them out. So that basically means that now we're using kind of, for lack of a better term, a real solution, right? And the real solution is something we're going to compute up above, right? So we're actually now tracking a solution over time, like for reals. And what you can see here is we do have a thing where we're, this is the actual Vox solution here. We do have a thing where we can sort of say, what do we actually want to have happen here? You can see the raycast. If I turn off this raycast, so let's suppose I just assume that all rays hit. And now we're just going to use this sort of voxel that remains over time. Then what you can see is, I don't think we actually do the motion copy yet, right? But what you can see is, other than the frames where the motion copy would be wrong, well, you know what? And it's never going to be wrong because there's no accumulation. This is just hard set every time. So we don't have to worry about that. What you can see is this version works just as well as the other version. So we know, at least for our current test purposes, there is no bug in the voxel to voxel thing. So the fact that we've got a stored voxel in the lighting solution, we're outputting that voxel to the card for interpolation. We're not really seeing any bugs there, right? So that's working okay. All right. So what's not working okay is our raycast here. All we're doing to test the raycast is just saying, look, if we were to take wherever we believe the voxel center to be, right? We do a raycast on that and where we believe the light, the direction we believe the light to be in. So we're saying, from this voxel center, we already looked at where the light was, and we did a subtraction to find that direction, right? We normalize that, and now we have a unit vector pointing towards the light source. If we call the Raycaster, as you can see here, and we look to see, is the distance we could get along this ray less than the distance that the light actually is? If that's the case, then unfortunately we've hit something, and so we can't actually provide the light in this case, right? So it's just a simple shadow binary, a Boolean shadow. Not really something we want to do in the future, because we want a rich, like, full bounce solution. So we're going to use the stuff we did before about actually convecting light around. But for testing the Raycaster, we would like to just start with a simple solution, which is just like, let's see if we can just say shadow on or off, right? And it'll be a kind of crappy lighting algorithm, but it's something we can more easily visually inspect. And what we see when we turn this on, right, is we get a pretty pockmarked version of this thing. And so if I run the thing, right, you can kind of see now that we get these sort of weird anomalies. And so now the question is, well, all right, what's busted, right? Like, you know, why are we getting that? And our goal here, again, is not to make this run because we care, because we don't care. This isn't the lighting we're going to use. What we're trying to do here is say, before we actually get into the weeds of like a rich lighting solution, which we know will be more complicated and which we already kind of wrote part of, and we're going to kind of move into that, what we're trying to do instead is just test the raycasting. Because since all of our lighting movement is going to be based on doing light tests to see if you can go from one place to another without hitting something, we need to first make sure that that's working. And if you remember correctly, we also have this ability to push debug lines. So one of the things we did at the end of the last week's, so it was 3 weeks ago, the last show we did, is we were drawing some debug lines so that we could actually see what we were looking at here, right? And if you look at, you know, it's hard to see because the lighting solution is actually being applied, right? But we can pretty trivially turn that off if we want to as well. But if you look and if you look at what we're seeing here, and you kind of look at the where the lines are being drawn, the lines that are being drawn are ones that are saying that they did hit something. So if you look where the code is actually how this path works out, what you can see is it's saying, look, if we are looking at a particular region, because if we don't want to draw all the debug lines, because this is a pretty big thing. It's what, 16 by 16 by 16 or 32 by 32 by 32. Is it 32 by 32 by 32? Anyone remember? Yeah. So it's a 32 by 32 by 32 grid. Now 32 by 32, when you say that, makes it sound pretty small. But when you multiply by 32 again, it gets pretty big, right? So voxels are cubic, not squared. So our intuition about how big they are tends to be sort of wrong, right? You think 32 by 32 bitmap, you're like, well, that's tiny, right? But 32 by 32 by 32, well, that's quite a few more, right? So 1,000 lines, not that many lines to see. 32,000 lines, a few too many lines to look at, right? So what we wanted to do, instead of drawing all the lines, which have just been a mess of lines, and it would overflow our debug buffers anyway, because those don't grow on demand. They're just kind of, fixed size or whatever. What we need to do is just, restrict how big of a region we're actually looking at there. And so what we did here is say, okay, look, inside the hot corners here, we're going to take the center. We're going to take -4 and +4 of the dimension. So we're just going to look at a total of like an 8 wide. Well, I guess that would be 9 wide. How do I think about that? I guess I guess it'd be 8 wide because I don't think we include. Yeah, we didn't. So right there, that's a less than. So we're just looking at an 8 by 8 by 8, right? So we're basically looking at that. Which is a much more manageable number of lines, and they'll only draw when they actually did hit something. So in the case where a debug line actually hits something, we will actually see it show up here, right? So what I'd like to do now is probably turn off the lighting so that we can not, so we don't have to actually look at that, and then dig deeper into these tests to see, are we seeing something that makes sense? Is this Raycaster just busted? What's going on? So inside our OpenGL, I'm just going to turn that lighting off for now. And I think we want this on a switch. I've been a bit lazy and have not been putting it on a switch here. I've just been kind of doing it this way, which is not particularly good. But if you take a look at what this produces, if we turn the lighting off and run, we should get, oops. Try that one more time. What we should get is something which doesn't actually show any of that lighting. It just kind of is a bright, full bright thing. And when we rotate around here, what you can see is you should see all of the lines that we drew that were casting lines and what happened to them, right? Now, if we look, and I don't know if we really can, but if we look in here, I'm hoping what we will see. Yeah. So if you look at what happens here, it kind of looks like these are correct to a certain extent. I mean, some of them at least look correct. Because if you look at all of these lines were casting up, and they do look like they stop right where they would have hit something, right? Like there's right where that thing stops. You can see it doesn't go through it at all, right? So all of these bottom pieces, like all of that, those all said, look, we couldn't, we weren't able to hit the thing. We weren't able to get to the light source. So all of the shadowing that you would expect to happen kind of all the way up through here does look like it is in fact happening. And furthermore, if you look outside here, right, you can see that the shadowing there also appears to be working, right? Those appear to be stopping right about at the edge, right? So all of those appear to be working. Now, there are some things, at least, from what I'm seeing here, that look like, they're not working. So, for example, right, I don't know exactly where this light actually is, but, if you look at where all these things are pointed at, it looks like it's right there. And that comports with what we set it to. We set it to where the hero was plus a little bit. So it's like just floating over the hero's head. So if I look, and I say, what's going on here? You look at these rays and you're like, what did they hit? I don't see anything. These lines are terminating in midair, and I don't know what they would be terminating, what the termination is actually resulting from. It looks like there's sort of a phantom thing here that they're hitting, and furthermore, that phantom thing doesn't even really look particularly obvious what the shape of it is almost. And similarly, if you look at some of these other ones here, I don't know what that is happening there. Just very strange. And so, I could convince myself if I was, trying to make excuses that maybe somehow we put in a collision volume for the lamp and it got output as a blocker or something, but that doesn't sound right. And as far as I recall, only actual visible cubes were getting sent down as blockers the last time I checked. So to me, this says our Raycaster is probably busted. And what we should probably do before we go any further is take a look at what's going on here and try to figure out why our Raycaster is so messed up. Now, there's good news and bad news here. I think the good news is if you look at this raycasting, maybe let me go in and do a slight change. In fact, I can just leave it running. Let me go ahead and say, when we're doing this casting here, let me cast all the lines really quickly here and just change the color. So I'm going to do a line color here, and I'm going to say that the line color is going to be this, or something else. So I probably can't do that. I'm going to say the line color is this, and then I'm going to draw it always, right? So what I'm going to do is I'm going to take this hit information here, and I'm going to change this so that we're actually just doing an if1. So we're always going to draw the lines. And then the line color is going to be based on whether or not you hit instead, just so I can see all of the lines now. So here's the line color. It's going to be set to this, and then if you hit, I'm going to set it to something else. So I'm just going to say in fact, maybe what I'll do is I'll just do it this way. So we will get a yellow line in the cases where we hit something, and we'll get a black line in the cases where we didn't, right? And so here you can see perhaps a more interesting version of the raycasting result. You can see very clearly where the actual light is now, right? And you can see that it's not the world's worst solution in some ways, because some of them look very accurate. Like that looks like a pretty accurate hit test. Maybe, well, no, actually it doesn't, now I think about it. That does. But if you look, there's a bunch of sort of incongruous things happening in the ones that don't hit as well. Because, for example, to my eye, I'm looking at that, that stuff in there, right? Some of these things that are protruding. And if I go inside here, you can kind of see like, all right, that does look like it's hitting. They're all stopping like right at the thing, which is even weirder because that sort of almost sounds like this part right here is wrong, which maybe it is. Like this T-ray less than light distance. I'm wondering if that's somehow incorrect, meaning the Raycaster is maybe actually producing somewhat correct results in certain cases that we are then saying aren't hitting. You know, so you see, there's just a lot going wrong there. It's not good. So let's start by going into Raycast and seeing effectively what's going on here. And what we may want to do is we may want to sort of extend out our notion of how we're drawing these debug lines. We may want to draw these debug lines like in the actual Raycaster itself as well. Or you know, output some additional debug information just while we're debugging this to make sure we sort of have a rough idea of what's going on in here. So if we look in here, how does this Raycaster work? Well, we start by doing some statistics. You can see in here we count some things. We don't really care about that right now because we're not looking at performance. So we can pretty much ignore that code. You can see that the way the Raycaster works, it's got a stack. This stack is for boxes that we're going to collide against. And the box stack is basically because we have what amounts to a hierarchy, sort of a bounding volume hierarchy, right, or BVH, that is based on rectangular solids. And what we do is we start by just putting the root box, which contains all our boxes, onto the box stack, and then we just kind of traverse through it, raycasting, going down as we go. So in order to initiate our raycast, we start by saying, all right, the T-ray is equal to the maximum T value you can possibly have. So that's like saying, look, let's assume we hit nothing. We just travel infinitely far along the ray that we're given. This is the direction. This is the starting point. So we're starting here. We're going in that direction. We start by assuming we can go infinitely far, just as far as we want. We then say, all right, let's load some constants we're going to need for some testing. I don't know if those are still needed anymore. We can check to see. In fact, you know what? I could check right now to see if they're needed because I don't know. We changed a little bit how this routine works, so we may not need the constants anymore. I'm not sure, so I may have defed them out just to see which ones are used here. So it looks like we don't use -1 anymore, but it does look like we use 1. So we then go to, let me just make sure that's true too. Just want to, yeah. So T close enough, what T close enough was, and I think we sort of turned this off, and we may want to turn it off again just for checking. But there is effectively a thing that we would do to, yeah, right here, where basically what we do is if we decided that this thing was like too far away for us to care, so, once we cast a ray more than 10 meters long, we don't go down the bounding volume hierarchy anymore because we just assume, look, this thing is too far away for us to really care. And so what we'll probably do is set this value to something that's sort of similar to our lighting fall-off rate. So when we do our lighting, like whatever the actual fall-off is for our lighting, we'll set that so that at some point we just don't care about the shadows very much, right? We don't care about the light motion around for things that are too far away because the amount of light they're able to contribute just isn't big enough, right? So then here we're going to say, look, we are going to pre-compute what the inverse ray direction is. That's going to be used for our box collision detecting. And then we're just going to go ahead and get started. So we loop over our bounding volume hierarchy by saying, while there are still boxes on the stack that we are supposed to be colliding against, we will pull the first box off of the stack, right? Like so. We will loop over all of the children inside that box, right? So like these are the things that box contains. And we will then do a collision test against the box. In order to do that, we load the box's position. And mind you, all of these are being done 4 at a time, right? And the way they're being done 4 at a time is we are testing 4 different light rays at the same time, right? So when we say we have a ray origin and a ray direction, what we're actually saying is, oh, actually we're casting 4 rays, hopefully roughly in the same direction, and we're going from there, right? All right. So when we come in here, we then say, and by the way, in our test case, we're only casting 1, because you can see in here, we just load up the exact same thing into all 4. So we're only casting 1 actual ray in here, but in the normal case, we would cast 4 at a time. Then that's for speed. That's to leverage the SIMD hardware. So we then compute the minimum and maximum box locations by adding the radius of the box, right, to produce the minimum and maximum corners. We then take the inverse rad. We basically are computing the minimum box, the minimum time to hit the box, and the maximum time to hit the box. Or I should say, we're taking the time to hit the maximum corner of the box and the time to hit the minimum corner of the box in each dimension. In each dimension. We're computing those by using the inverse of the ray direction here, right? So 1 over the ray direction. And again, the reason for that is we're trying to do a fast box collision. So we're trying to avoid doing divides here. So we pre-divide that ray direction, and we do the Hadamard. So we just do the vector Hadamard product to get what we think those t's will be. We then take whichever one of those is the best, right? So the one that we would hit first, and that's done by a series of min and max steps. So we say the minimum is going to go through here. So we take the T-box min and T-box min. We take the minimum of those. We take the maximum by doing the T-box min and max maximum. And then we take the T-min and the T-max, which is the earliest we hit and the latest we hit, by, again, taking the maximum of the components of those, right? And then when we're done and we look at like what the maximum side is, we just see, look, when we were to hit the, if you think about what this is doing, it's saying we have a ray, we have 2 t values, one where it enters the box and one where it exits the box, in a sense, right? If the place where we exited the box is less than 0, that means that the entire box is behind where we're casting from. So we would not, that's what this anyTrue is here for, we would not want to consider this box as something that can produce a usable collision, because it's behind us. And the reason that we can have that happen is because math doesn't really work particularly well on things that only go in one direction. Not the band, but actually just in one direction. And to be honest, I bet the band one direction is not very good at math either. But in this case, what we're saying is, look, we need to know the t values along this line, and then what we're doing is saying if they're less than 0, then they're behind us because we're talking about only one direction. So that's what's happening here. So this is the first test that says, okay, we don't actually want to know about collisions that happen that aren't even the direction we're looking. We then say, all right, now what we need to do is say, are we inside this box? And what we're trying to do here is say, look, if anybody who was correctly on the correct side. Now, you might say, what's this for? The reason we have to do these extra checks is because, remember, we're doing 4 rays at a time. So max pass may have resulted in true for only 1 of those rays, and the other 3 may have been false. So what we need to do is say now, are we inside anybody? And the way we would know if we were inside is, did anybody pass on T-min, right? Where T-min was behind us, but passed on T-max. So T-max is in front of us. That would bracket our starting location. So the origin of the ray would be inside the box. That's what this is saying, and that's why it's called T inside, right? It's pretty well labeled. Good for us. We then look at T-valid, and what T-valid says is, all right, if T-min is ahead of us, and T-min is less than T-max, so it means we're not in some weird, like, inverted space, where, we didn't really register a proper collision or something like this because, one side hit something and the other side never hit the other thing or who knows what. So if we're actually in a case where like the Tmin is less than the Tmax and the Tmin is greater, right, than 0, this is a real hit. This means we looked at a direction, we did hit something, and we now have the T value in Tmin of what the hit actually was. So at Tmin, we hit a box, right? The mask is just something that's telling us whether or not this particular hit that we found, if we found one, right? That's why we're ANDing with T valid. The mask is just telling us for this particular hit, are any of them less than the actual ray we found so far? Because remember, we're going to test tons of boxes. T-ray starts out at F32 max, so the first time we find a valid hit, that will actually, be one we take. But then every hit after that, we only want to accept a Tmin that's less than the hit we already found. Because otherwise, we'll actually be moving our hit further away, right? But the closest hit is the one that stops the ray. So this test here is used to figure out which one actually, which hits are actually new valid hits, and which ones are hits that happen past the closest hit we already have. Close enough, again, is just saying, look, if we have a new closest hit that's closer than a hit we've already had, and it's close enough that we would descend through the hierarchy, then we're going to want to descend, right? And that's what we do here. Box child count is saying, okay, look, if anyone is inside this box, right? So we raycasted from inside it, right? Or anybody was a close enough hit that it's probably within our best. It's probably in our best interest to descend because this box is within our threshold for where we want to start. Where we want to keep looking, right? Then we go ahead and continue down the hierarchy. Now, to be honest, I don't think this is not probably the metric that we want. The reason I don't think this metric is the metric we want is because T close enough should probably be based on how big the box is. So we probably want to go down the hierarchy based not on just a fixed value, but on how high up the hierarchy this box was. So I would probably say something like And so what this is saying is essentially, when we do this raycast, if we're right next to something, obviously we want to traverse into its children and see what the specific hit is. But if we're far away from it, well, how detailed was this box? If this is a fairly detailed box, meaning we've gone down the hierarchy like 1 or 2 steps, if we're, only maybe 10 units out, we should probably still traverse it. If we're 20 units out, maybe we wouldn't, right? And then as we go down further, if we're like 5 steps down the hierarchy, maybe now, even 30 steps out, we wouldn't traverse it, right? So I think we want that, that level of detail parameter to be based on where we are in the hierarchy so that we open up boxes and look at them more or less as we get further away, more continuously, and not just like, all right, everything within 10 units gets done exactly, and everything outside 10 units doesn't get done at all, is not a very good it's not a very good level of detail policy to me. So I think we want to look at that, but that is not probably related to our problem here, because unless I'm misinterpreting the meaning of 10 units here, and there's some kind of scale that I'm not thinking about that's actually in play, 10 meters is way longer than those erroneous ones we were already looking at, which means that our bug is not really related to this. We have some other bug, if I'm interpreting that right. If I'm not, then that could very well be implicated in our bug. But so then we look and say, if we're going to traverse, we do, right? But if we're not going to traverse, then what we need to do is see if any of these rays actually want to be recorded. If any of the rays actually did hit, then we're in good shape, right? We kind of know that we want to keep going. And what we want to do here is say, all right, we're going to accept all of the new T-mins that passed our mask test. So the valid hits that were closer than hits we already have, we are going to accept them. We're also going to record the center, radius, color, and emission of the box in that case so that later we can do our actual work on it. Now, again, one of the problems here is we're not really recording the normal, and that was the problem that we had before. I'm not sure how we're going to deal with that, to be honest, in the future. We may just not. Where's my... Do I not have tissues here? Oh, tissue fail. All right. That's very sad. Before I forget, I'm going to make myself a note. Streaming setup needs tissues. Note to self. Good thing it's not allergy season, or that would have been a real problem. All right. There we go. And so what I'm more or less doing here is just saying, look, take the parts, for all our 4 arrays that we're casting, accept anybody who is the new closest hit, and you can see us kind of doing that there. And what we're going to do about the normals in the future, I don't know. We store those center and radius so we can recompute them, but it's kind of hard to recompute, and, we'll see. Previously in the code, we had a thing here, and you can see me putting it to do in there where we said, look, if everything in the mask is true, right? And what that means is that this particular hit all four arrays hit the same thing, right? Then for some reason we would break out. Like that would be it. I don't understand why. I don't understand what that was for. I don't even know why you would ever care about that. Like, I can't even really tell. I have literally no idea why that would even be a condition we thought we should be checking. Because it's effectively saying, look, is this particular set where we hit all these things? We're leaving the loop here. I just have no idea why we thought that was good. Maybe we were trying to do something like saying, look, at some point, we know that all of the boxes that come next have to be further away than we are, right? So we can leave the routine at that point and not worry about it. I don't see how this condition isn't that. It's not even related to that. So I just feel like this had to be a case of us being dumb. Someone on the chat can tell me if there was some better reason for it. But I think that was just wrong. I can't see any reason why this would ever produce a reasonable result. And what I assume was happening here is I assume this case was effectively never occurring. Because when we would actually cast 4 arrays, we had not actually put in coherent ray selection at that point. So we weren't sending them out in similar directions at all either. Which basically meant that we would probably never, in one hit test, one box, would probably never stop all 4 arrays. Or at least almost never stop. So we probably weren't seeing bugs related to this only because it never actually did anything. That's my guess. So I'm going to go ahead and delete that because I can't see any reason why that would actually do anything useful. But my feeling on it is that there could be something done here where we do actually check. For example, let's suppose we took T-Ray, here. We could do a check. In fact, I'll put it to do here. So basically what we could do here is say, hey, we know what the T-ray values are so far. What we could do is say, test to see whether or not anything in this parent box could ever possibly be closer than what we've already got for our 4 arrays. And basically don't process it if it isn't, right? If this whole box is further away than where we've already found our closest collisions, we don't need to look at it, right? Because all we could ever find is collisions that are too far to be accepted by this, right? And so I do think that is pretty important. In fact, I think that's something we should just do. Like, in other words, I guess we don't even need that. It's just mask. So correct me if I'm wrong. I mean, just hear me out here. This really should just be here. Well, like this, meaning obviously any closer, oh, sorry, not quite true. So if we're inside, we need to do it. If we're inside or we are close enough and could be closer than the current hit, right? So if there's a child count, and we are either inside the box, in which case we definitely have to do it, or we are close enough and the possible closeness of this thing could result in an actual hit we accept, then we would traverse down. So I would argue that's almost certainly necessary, because otherwise we're going to waste a bunch of time processing boxes that we didn't need to, because they couldn't possibly produce a hit we would ever actually use, right? So when we hit the bounding box of the parent bounding box, if that hit isn't closer, certainly none of the things inside it could be closer unless we ourselves are inside it, and that's a test we were already doing, right? So I'm going to go ahead and say that has to happen, right? Then we can go on in here and say, all right, now we're going to do the acceptance test and record the fact that we used a leaf here, and off we go. Right? So then we come down here and we say, all right, now we actually have to compute what the heck happened. We take a hit position and we compute that by taking the ray origin, adding the ray direction times the distance we went. We then do a bunch of work here to try and reconstruct the normal. You can see that being reconstructed here in a pretty janky way. It's not good, right? I don't really know. I mean, I don't really know. I don't really know what the best way to do this is. I really don't. So this is probably janky, but this, for our current purposes, we don't have to care about this at all, because the only thing that we need to know is that the hit P and the T ray, right? Those are the only things we're really caring about at the moment. And so if you look at this equation here, this is the only one we're actually using, and that's the origin plus the distance we thought we went times the direction equals the location we believed to have hit. That's the only part we care about. The rest of this stuff is for computing the normal, which we don't actually know. is correct or not at this point, and we don't care because we're not using it for anything. So we will care eventually about that, but otherwise we're fine. So if you look at what this is doing here, I guess I would say so far, walking through that routine, other than the fact that I think there was an inefficiency there, like we should have added this, right? But that's just for efficiency. I didn't see the obvious bug, right? Like I didn't see an error in there. And so I don't really know what our issue is. And we're going to have to dig into this pretty hard, I think, to find out what's going on. All right. So if we look at what we're seeing here, I think the first thing I need to do is try to isolate myself down to a raycasting case that I actually know specifically which one it is. And so what I'm going to do, because this is casting thousands and thousands of rays here, tens of thousands of rays every frame. That is not going to cut it for debugging, right? I'd have no idea what I was looking at. We would be stepping through the thing forever. It just wouldn't help. So I think what we want to do first is isolate a particular case, just one of these. And it just so happens, I think there's a pretty easy way for me to do that. I can take a false positive, so something that was saying it hit something and it definitely didn't. This yellow line right here, that's not that hard to figure out which one that is, because if you look at where it is, it's on the outside of 2 dimensions and it's 1 down from the top, right? So if I was to pull up into my voxel code where I'm already trimming the debug lines, so let me go ahead, oops, that's not good. Let me go ahead and actually jump to that code that's outputting the debug line. And what I want to do here is change this from doing a regen, right? So I'm gonna keep this code around in case I want it later. But what I'm gonna do instead is I'm gonna make sort of a special purpose version here, where instead of this, and I'm also gonna put this out into a tester here, where I do like B32 is test cast, right? And I'm just going to record a very specific one of these. So what I want to do here is delete, the bottom half of this thing, and just look for one specific one of these. And so what I want, I think here, is I want to look at the furthest in like X and Y, and then like not quite the furthest in Z or something like that, right? And then I'm going to say, all right, and in fact, what we could do too here is I could make this actually be I could make this actually just be if is test cast, and then we'll just capture this range query into this, right? And so that way, now I have an easy way of isolating a particular line. And the reason I'm doing that is because I want to be able to set up, this sort of nice, is this, yeah. I want to be able to set up this sort of nice test case where I know exactly which line it is that I'm looking at, so I can step through it, right? And so if we look at the code here and I run this now, I want to go ahead and see, oh, it looks like I picked the wrong Y. So actually, no. It was the furthest back of the Y. I don't know why I stopped the program. I always forget that the hot code reloading will take care of a bunch of that stuff. And so it looks like we bingoed out on that, right? So there's a single test line being drawn, and it is wrong as far as we can tell, right? That does not look valid to me, right? So now what I can do is downshift into debug build and actually step through and see what the hey is going on there, right? And so in this test cast case where we do this line here, I can now do a breakpoint right before I go to cast. I can do a breakpoint on that test cast and know exactly what I'm getting. So like this. I can just put a line of code there that I can stop on if I choose and step through the actual caster to see what it's actually doing. You know what I mean? So as we run and produce that erroneous line in the slower build now, you can kind of see this happening, right? The Raycaster is super slow, right? If you don't run it in release mode, right? Because yeah, I mean, it's doing 32,000 things. So if each one gets a little slower, it will slow down quite a bit. But I don't care because I don't have to do anything in this mode. I just need to know about that Raycast. So if I now open up the lighting code here inside the debugger, which will be there, I can go to that piece of the code and set a breakpoint effectively on that test, which is right here, right? So what I want to do now is go, all right, stop there. And this is, in theory, our erroneous test. So this is the one that's going to think it hit something, but it never actually hit anything, right? And the first thing I would like to do is I'd like to know a little bit more about the actual case first. So before I even step into it, I just want to look at what these are, right? So we have a hit value of 1, which is what we'd expect. How far away was the light distance, right? So in this case, it's 6.5 meters away, theoretically. If we look at the casting information, and we look at what we're getting for T-ray, you can see that we're getting something significantly closer than that, right? It's saying that it only took 4 meters to hit something, and in order to get to the light, it needed to travel 6.5 meters, right? So something's fishy there. Not good. Now, we don't know much more than that, because we can't really see the diagram. What I will say is 6 meters, I guess that roughly comports with, I mean, I think our game scale is maybe not quite realistic in terms of meters, so I shouldn't say meters because it's probably not really meters at this point. But, is that completely ridiculous? I'm not sure yet. But that's what we're being told. If I rerun the loop again so that now I can step into the Raycaster, I'm going to look at what some of these values are more specifically. So what we're going to do is we're going to start off with the root box, and we would expect to traverse down the root box. So I'm hoping that we hit this case here, and we do, right? So we push that box down on the stack. And then we'll have to see, in here we missed this case, and I'm not sure why. Let's take a look at what this box says. So this is a bounding volume used for, it is actually containing subvolumes. We rejected it. I'm not sure why exactly. But in fact, you know what I might do here before we continue down this route? Let's pull those out into Booleans we can see, just so we can inspect them more easily. So if I jump to the Raycaster, I don't know why I'm not just jumping directly to it. If we actually go through here and just set up some Booleans here, now I can see exactly why we went into this. So by looking at the child count, the any inside, the any closer, and the any close enough, I can see specifically which thing caused us to traverse down into it or not, right? Or to skip that case. So let's try that again. And now let's go back. Stretch. Okay. So in here, I want to break only on the test case. So I'm going to skip those. I'm going to go into the caster. We're going to watch ourselves go down the root box first. So that's there. Then we're going to go, and maybe I'll set the breakpoint now. All right, so that one failed on max pass. So that was weird, wasn't it? I mean, that was different than the last time. Oh, you know what? So we do have one issue here. That is, I guess I don't know if while this camera moves, are we going to get different results? Because is the voxel moving with the camera at all? It might be. So one thing that we might want to do is, I should probably verify whether that's true or not. But what I was going to say is we might want to make it so that the camera starts off at a known good location so that we don't do that sort of interpolation. I just don't want to have a situation where I feel like we need to skip the first frame, I guess is what I'm saying. So let's do that. And maybe I'll put a piece of code in there that skips the first frame so we don't have to do it manually. All right. Now let's go in. So in theory, this should be the same as before. Excuse me. So there's us going down the route. And there's us skipping max pass on the next one. So this is the same as it was before. So okay, I'm not sure what's happening there exactly. So those all fall out of scope. I wish you could still inspect variables. I know George did a little bit of work on that, and so now you can inspect variables on the closing brace, but only on the closing brace. All right. So we're traversing this one. Let me just put these up in here. So you can see like all of them, I guess, are close enough. Let's actually view these values too. So if we actually look at what these values end up being, oh, and the mask. The easiest way is probably just to look at like, yeah, like one of these. So maybe what I'll do is like mask.u32 0, like so. And I don't actually know how to, there we go. I'm like, I want that to be in hexadecimal so it's easier to see. So this value should be just FFFFF or 0, right? Like all these masks should evaluate to all ones or all zeros in general, I believe. And so if we look at these, like all of these computations here should probably be expressed this way. So we can kind of see like what we're looking at here. And then these should correspond like with it. What is, it's not T closer, so. So any closer is just the mask actually. Yeah. All right. So that's really what we're looking at here. So these should probably be reordered. So we've got any inside, any close enough, any closer. So you can see here, here's our values, and they're doing exactly what we'd expect. So extracting the mask out here is working properly. It does exactly what we think it should do. And so nothing particularly weird there. We can also look at the box child count to know if this thing is, you know, basically a container node. And so as we're doing these collisions here, we can also take a look at like the tmin value, which is the primarily important value here. And I can just look at the tmin. I guess I'll just do like the .e 0 value there. And I'm going to look at the T-ray as well, which is our current best. So you can see in this case, it's like, well, anything is going to be better because currently we haven't recorded a hit yet, so anything is going to be better than that. Here's where we believe our hit to be. It would be nice if I had some way of really figuring out where that was, like, but you know, this is one of the problems with this is I don't know if there's much of a way to do that. So I'm gonna like step through this, sort of gaining a little bit of insight here. But then what I'm probably going to do is augment this with some drawing calls, because since debuggers today still can't do much drawing, even Remedy, unfortunately, can't draw out things for us, it'd be pretty hard for us to know how reasonable these values actually are, because they don't look obviously wrong, but they could be subtly wrong. You know what I'm saying to you? So here we go again. We're hitting a node we're not going to descend, right? So there's two children in this one, and we're not going to descend into it. So we're going to use it as an actual collider. We're going to see here that means that something was closer, and we're not inside it, and it wasn't close enough to descend, right? So if we look at the actual hit, it's at 11. And so we don't actually care, like that's not the hit we ever end up recording. We know that that's not the hit. So we don't really have to worry about that one much. Oh, let me put the depth up there as well. So we're currently just at the top. We don't have a stack right now. There's just this one. So we don't need to traverse that guy. Wait, in that case, how did we... If we were already on depth 0, how did... Oh, because we're still looping through children. Sorry. There. So we're still looping through the children of this, and so this one must actually be what we wanted. So you can see here we're taking a hit on the t-valid there. We're getting sort of a we probably tested two sides of a split basically, and we're traversing the near side of the split. So we should probably, we're probably going to do that for a little bit. We're traversing down and getting the near sides to sort of get down to the place where we actually are here. And then at some point, we should actually start hit testing somebody. I don't know how far down our bounding box hierarchy goes, but it's not a very good bounding box hierarchy, by the way. All right, so here we're recording another hit. You can see in this case the actual hit that we wanted, or the actual hit that we took, right? Now, if we look here, this is an actual node. It's not a container. So we are recording what we believe to be a valid hit of an actual box. We think that box was close enough. We are not inside it. It is less than 10 meters, which is true. It's closer than our current hit, which was also true. Of course, we just overrode it. And we're keeping it, right? That there is the actual, the only thing we could really say here, because everything looks correct. So the only thing we could really say there is either we have put in a box that is actually here. So the box is erroneous, right? Either we put in an erroneous box and are correctly hit testing against it, or we did put in the correct boxes and this code is erroneous, right? This part right here that computes the t. Because this part looks like it's working correctly. This t-value is the closest t-value. It should have been recorded. So the only way that we could really have gotten this wrong is if these values coming in are wrong, so this p and radius are wrong. And like I said, that's why we're going to have to start drawing this, because if we look at the box p and the box radius here, we're not going to see anything, right? I mean, okay, it's a 0.5 by 0.5 by 0.5 box, right? Do we have any boxes like that? I don't know. Like a 1 meter by 1 meter by 1 meter box, right? Has anyone put one of those in? No idea. Maybe they have. I don't know. So we don't really know, but we know that someone put it in there. Is it reasonable or is it not? We'll have to find out. And then this is the location of the box. Again, reasonable or not? No idea. So I think what we need to do is draw these boxes, okay? So we can see what we actually hit tested against. So what I'm going to do here is inside the Raycaster, I'm going to basically have a toggle, a runtime toggle, that's like debugging or something, right? So in here, I want to have a debugging just for our purposes right now. I'm going to turn that on when we're doing just this one pass. And when I'm doing that pass, then what I'm going to do is I'm going to push debug lines down to show us where the actual box is, right? So the way I'm going to do that is just do if debugging. I want to draw this box. I also probably want to say which kind of box it is, right? Maybe I'll do it this way. So I'm going to take a box. If it has children, it's going to be purple. If it's not, it's going to be cyan. So the cyan boxes are going to be ones that we actually test against. And I want to draw these things. You know, I might even want to do this a little bit fancier, right? So I might want to do a thing here where we say, all right, set this box color up here to black. And then maybe what I actually want to do is just set the box color inside to different things. So if we look, let's say we're going to traverse down this thing, right? We're going to set it to a new, we're going to set a color here. Or if we actually hit this thing, we're going to set a color here. So if we traverse down it, we're going to set it to purple. If we don't, if we hit it, we're going to set it to yellow. And maybe we might want even more than that later, but you know, for now, we'll just leave it at that. And then what I'm going to do is I'm going to push debug lines down to just draw the box, right? So if we look at the push debug line call, we just need to pass the lighting solution, which we have. And then we're going to have the from P, to P, and the color. So we know what the box color is because we already put that down. So we just need the from P and the to P, right? And so to do that, we kind of know we can draw this by just using the box P and the box radius. And we computed the box min and max. So I'm going to use the box min and max since that's something we actually have, right? So box min x, box min y, box min z, like so. We're going to go, we're going to use this like so. And we're just going to draw the debug lines that constitute the edges of the cube. So we're, well, of the box. It's not a cube. So if you think about how to draw the edges of a box, right? Well, we know that we've got 6 faces. We know that we've got 8 vertices. And we know that the edges that connect them, right? We have 4 edges around one side of the box, 4 edges around the other side of the box. So that's 8 edges. And then we have 4 more edges that connect those 2 sides, right? So we know we're going to have 12 lines to draw, right? And those lines go, you know, between the mins and the maxes only, but different combinations of them. So for example, if I just wanted to draw one of the rings, I could say, well, let's draw the ring around box min x. Then what I would do is say, well, you know, okay, we go from min y to like max y, from max y to max y, max z, from max y to max y oops, back to min y. Is that right? Yeah. And then back to the min, right? And so now what should happen is if I want to turn this on, and what are you complaining about? None of the overloads convert all of the types. Oh, right. So yeah, that's a v3, so I need to extract just one component of this. I assume I can do that. Just test, see if that works. Yeah. So I should be good now. I'm just going to go, oops. Let me get out from behind my now smaller head. And I do need to get the push debug line call up one, because we're now calling it from inside the Raycaster. All right. So now if I run it, what I should see is one ring, you know, for boxes that I'm drawing here. I should see one ring. I'm going to skip stepping through it here. I just want to look and see what it draws, right? I should see one ring for each box as I process it if I turn on that debug flag. So right now I'm not seeing anything. I'm going to go over here. I'm also going to, I don't need to be in debug mode for a while. While I'm looking at these diagrams, I can just do it directly. So where we call this raycast function now, not there. That's the regular one that we're going to try and get to eventually. I'm just going to pass true for debugging. And so now when we actually build, we should be able to, oh. You know what I just realized? That'll draw way too many lines. What I meant is test case, because I only want to draw them on the test case. Sorry about that. Forgot about that. I was just like, oh, we want to draw them. But I only want to draw it on the test case, so there'd be way too many. So what you can see here is we're drawing the boxes now, right? But we're only drawing like one ring of the box, right? Right away, you can see there's some weirdness going on here, right? So that's not probably good, but you know, let's finish drawing this first and we'll go from there. So gonna jump back to the Raycaster. Don't ask me why I closed the program. In fact, we can just leave the program running. And in here, I'm just gonna draw the rest of these, right? So there's our box min and max stuff. Let's draw one more ring. Oops. So this is just the corresponding ring. So now it should draw 2 rings per box. There you can kind of see them happening there, right? And some of these make some sense. Like those look like big bounding boxes, which is what we would expect, right? Others, not so much. Like I'm not sure what that box could be. And that kind of suggests to me that our box positions are bad, because if you look at what's going on there, like it looks like it's hitting a box that actually does exist. So that suggests that our box P is wrong. You know what I mean? Like we got some issues. That's fine. We'll deal with that in a second. But you know, let's finish drawing our boxes first. So then we'll come through here. I'll draw the last set. And what this is going to be is this is just drawing between the min and max x. So that means that here we're going to keep the same thing for each of these, right? So we're going to do min min, max min, max max, and max min. Yeah, sorry, min max. There we go. And here we're just drawing between the x rings, because we drew one ring around min x, one ring around max x, and now we just need to connect those two up. And now we've got a full box drawn. So now, when the live code reloading reloads the changes, you can see here now we've got like boxes. And like I said, some of them look correct. So like if you look at the bounds here, it does look like we had a box that contained, well, you know what? I'm not sure. I guess I'm not sure why this region doesn't look contained. So I will say I'm a little weirded out by some of this, because if you look at what's going on, like some of it looks pretty good. So, right, you've got like boxes here and here that appear to perfectly bound the world the way I would expect, but there's nothing containing this part of the world over here. And if you look at the lighting bounds, anyway, the lighting bounds at least do extend out to there. So I'm not super sure. Oh, you know what? No, it's okay. It's just faint. So there it is. You can see there's a black bar. Okay, so it is, they just weren't traversed. So that's fine. All right. So if you look at the hits here, you can see we hit this one because it's too far away. We did a hit against that one. We then sort of traversed down. You can see exactly the pattern here. We kept traversing down. We've got people who are enclosing our light cubes. And that doesn't really make any sense, but that's what was actually happening there. This cube, I don't know what the heck is going on there. Let's try to determine which kind of box that is. I don't know where that box is coming from. It doesn't look like a bound. So it looks like a box someone actually stuck into the system that's at like just the wrong place. Yeah, you got me, man. So we come in here, we're taking a look at this box here. What I want to do is say, okay, this box color is going to come out as 0, 0, 0. And then when we come in here, we're going to set it, if we're going to traverse it to this, or if we hit it to this. What I don't like is if we hit the box, I want to know whether or not it was an actual aggregate box or not. That's the thing I wanted to know. So basically, like in this case, I want to say if it had a child count, I want to see one thing, and if it wasn't, I want to see another thing. So what I'm going to do is I'm going to set it to cyan in the case where we like if the box in question is actually a container box that we are just testing against because of the farness or not furthest away. And then I only want to see as yellow. So you can see that happening here, right? Like that was a box that we just said, well, it's too far away, so we test against it, right? If it's a box that's close enough to be tested all the way down and we hit against an actual box in the end, that's right here. You can see that happening. So something's busted. That's just wrong. That's saying that there was an actual physical box placed there by the game, and it is asking us to collide against it, right? Furthermore, our light probes themselves, because they are... that would explain a lot of that pock marking as well. Our light probes themselves are actually considered colliders. That's a mistake. We didn't want that. So we should probably go ahead and eliminate those as well. So, like, that has to happen. So yeah, we got a couple different things we got to do now. Let's start by removing those from the system and see what happens. I'm not sure. And then this will probably remain, and then off we go. So in the push cube call, you can see in the push cube call, we're passing this down here. And we don't really want that. Like, we don't want this thing to be an actual occluder. I don't really know how we want to handle that. I also don't know what the Z bias needs to be there for anymore, but I guess we were doing some stuff with that for rendering purposes. But I want to look at the places we're calling push cube, because I don't think there's that many of them. And what you can see here is, if I go global on it, the places we're calling it, like other than the render test code, right? Inside, like, yeah, inside the asset rendering and the entity code, you can see exactly where they're being called. I want to know which ones of those actually want collision geometry, right? We don't care about that. We don't care about this stuff. And what I think we might want is like an actual occluder call here, right? Yeah. I mean, I guess what I would say probably... I guess what I would say is probably what we want here is something where only, you know, where we only push occluder stuff on when we actually wanted to, right? Because I can turn that off, but what I really want is like only these things would have occluders on them, right? So when we call push cube here, we would say like, you know, a flag or something that says that this thing is going to be an occluder, or, you know, we do like that there, right? Because if you look in push cube, this is the only code that actually cares about it, right? So I kind of feel like that code really wants to be its own path. So I think I might do that. So in here we would say like, look, get rid of this, right? Have a thing on here that's like that. And this will actually be the code we care about. So we'll say, is the lighting enabled? If the lighting is enabled, we'll, you know, do what we have to do here. We need to know some stuff, like we need to know what the color is, so that's got to be on there. We need to know what the P and the radius are, so let's get those on there. But other than that, I don't think you really need to pass much. And this way we'll only do it when we really actually need to, right? The texture index, I don't know if we actually want to ever use those. I'm going to go ahead and guess that we probably don't really. I think we can't afford to do texture lookups in the Raycaster. So I'm going to get rid of that for now. And I'm going to say that we just really have that P radius ref C is all we're going to actually initialize. Right? In fact, I could leave these in here temporarily, but I think we're going to want to get rid of these. Right? Like so. All right. This will literally just push exactly the same thing, right? So I'm gonna put these into variables that I can pass to both. And then we're going to try and figure out what's going on here. So, yeah, what are you complaining about? What is emission supposed to be? Is that just a single value? Yeah. All right, so render group, p-value, oh, and then it needs the color. And then we're good to go. And now we shouldn't have those bounds anymore. Yeah, and we don't, right? So I think I mean, I guess that's good in a sense, but I probably need to now that I have that, which I need working, I think I kind of temporarily want to re-enable it though, because I need to debug that sort of bad case, right? Because that case still looked wrong, and I just kind of need it to still be doing what it's doing so that I can figure out why we actually got boxes placed in those locations for no apparent reason, right? And I'm not sure, yeah, like, let me turn on lighting briefly so I can also just see what our current status is, because I'm not actually sure what that will look like either. But if I go ahead and recompile this guy, that seems nonsensical. So now you're telling me there's no lighting? What am I missing? Oh, that's not what it's saying. That's just because we zero everything out. So yeah, in this case, we're not actually doing the test for whether or not the thing actually hit. So you can see here, we would still need to do this, right? So that makes more sense. So I just want to see what happens so I can know to what extent we're getting erroneous raycasting now versus not. So it looks to me like we're still getting those erroneous cases. They're different now, to be sure. But, you know, it's still kind of a little odd, right? What we're seeing there. So I guess what I could do is double check now if I can just switch back and debug a different ray case. So let me look really quickly and see if I can just debug a different one first. Because if I can, then it's good to get those extraneous things out of the tree so I'm not like constantly wondering like why is there this little box there or whatever. So I would like to see if there is a way of easily now without those seeing the same error and then picking out a new test case. But if there isn't, then we'll just regress to the previous test case, right? So let me just see what's up there, right? So I'm going to look at this case. And now we should see another one of those now we should see another one of those sort of exploding balls of lines like radiating outwards like a little sun, right? And what you can see here is looking at, you know, what we're looking at here is all of these are showing up as black, which doesn't make a lot of sense because they should be hitting something, and the fact that they're not is not a good sign, right? So looking at, yeah, like, you know, now we kind of have a weird, and I honestly, I'm not sure why we are even seeing what we're seeing here, but if you look, right, you're seeing like some of these are hitting something. That's very peculiar. I'm also not sure, wait, are we having some kind of compile error here? Like, why is the lighting, oh, right, because I'm an idiot. Let's try recompiling that again. So if I look now and I should see more things getting hit. You know, I really don't. So, yeah, I guess looking now, I'm having trouble now seeing error arrays. I want to try and find like errors. And if you look, I guess I would say the error now mostly appears more to be things that are saying they aren't hitting anything. Right? I mean, a lot of these should probably, there should be yellow lines coming out in this direction. Like all of this stuff should be hitting and isn't. Right? So if I restart and just look at the startup location, I should be able to pretty trivially find one that's erroneous, right? Like one that just thinks it didn't hit anything, but definitely did, right? And it's a little hard to find because it's you've got to kind of look inside. We almost need like a wireframe mode for looking at these, because figuring out something that's sort of inside. Those look like they're stopping right there too, like as if they did hit, but they're being drawn as not having hit. Very confusing. To be honest, I have no idea what I'm looking at right now. This makes no sense to me, what I'm viewing. I mean, so, like that all looks correct, right? I mean, all of those things correctly cannot hit the light source. So that's not weird. But like all of these, I guess, are they just happening to coincide with like, no, they can't possibly. I mean, this doesn't even make sense. Like, these are supposed to be casting from voxel centers. How on earth are we getting these values? Like something's up. Let's take a look. So this hit value here, where we're looking at the T-ray value and comparing it to the light distance, that's the thing that's telling us whether we hit something or not. Whether we hit something before or after the light source. And the way we're drawing it is we're drawing it from wherever the casting start was, right? And then we're drawing it to wherever the hit was reported. We shouldn't even be able to be producing those lines. Like the lines we're producing don't even seem like we shouldn't be able to be producing those Vox center P's in the first place. So I'm super confused right now. And maybe I'm just misunderstanding something about how sparse the voxel is, but it doesn't make sense. Like, let's suppose all we did was just show the voxels. So we took the Vox center P and we did a push debug line on it. And like, I'm just going to literally say, all right, forget about where you were drawing it to. Just take the Vox center P value and add some very small number, right? Like very, very small number in Z. And just so you're basically just drawing a tick mark, right? And that's all I'm asking for. So we're not actually drawing a raycast line anymore. Just draw those tick marks, right? And so if you look at where the tick marks actually are, right, those are the casting locations. And so just based on that, like how are we getting those lines we were seeing? It doesn't make very much sense. If I leave those on, so let's do this. Here's the tick marks. Now draw the cast lines. I should only see things coming out of tick marks, right? There should be nothing coming out of a place that doesn't have a tick mark on it. We can make this a little bigger, like so. So you can see that the tick mark shows me where the thing should have started, right? So first of all, like total nonsensical results, this right here, like doesn't have any line coming out of it at all. So that doesn't really make any sense. Furthermore, like there's like lines that appear to go nowhere. Like that line literally stops right there, right? And there is no tick mark for it, period. So something is very wrong here. So the next thing I guess I want to do is I want to draw a normal. So if I go ahead and take this case here, and what I want to do is say, all right, like here's the tick mark that shows where it is, right? And then let me also draw like something that tells me what direction it was trying to head in. So there's this light normal N, right? And so what I want to do is draw a small directional arrow in the direction of that light N, right? So we've got what amounts to, let's see, a purple one here. I'm going to go ahead and put that in like so. And I will draw a small normal in that direction. But something's busted now. So we need to like fix this, whatever we're seeing here. We need to make this congruent first, or we're not going to get anywhere. So here's our debug display, and you can now see that we've got like, you know, which direction we were casting in and the tick mark. And so, I mean, this is just a garbage situation that we're getting here, because we're getting a cast, like somehow we're drawing stuff that totally doesn't line up with what we think it should be, right? Like, I mean, these are the locations we're supposed to be casting from. What the heck is all this garbage? It doesn't even make any sense, right? You know, if I look in here, we're not even getting a line that's coming out of there. And what's even weirder is we know that these lines have to start from Vox center P. So I am totally confused now. I'll be honest, I do not know. I do not know how we're seeing that result. The debug lines all start at Vox center P. These two are correctly starting there. This one somehow is not. So let's go ahead and isolate one person and find out what the heck is happening. So if I look in here, I'm going to do the same thing I did before. I'm going to try and pick whoever the easiest person is I can pick. And I'm going to try and figure out what the heck is happening with them, right? And one thing that's kind of nice is I'm looking at this guy right here, right? And there's nothing emanating from him at all. At all, right? And what I would expect to see is I'd expect to see the line like hit this thing or something, right? I don't know, but not this. So let's pick him out because it should be pretty easy to pick him out. He's on the edge. That'd be +3, +2, +1. So I should be able to pick him out by just doing this and changing this to that. I believe that should isolate this dude right here. And then we can just see what's happening, right? So here's a dude who's trying to cast back in that direction, and we get nothing. There is no debug line at all that I can see anyway for this cast. I mean, I see nothing. I don't know about you folks, right? So there's nothing being drawn at all, and I have no idea why. So what I'd like to know is, in this test case, how is it possible that this hit, this cast T-ray value is coming back so bizarre, right? And what I want to do is maybe convert to debug mode and actually step through this case and find out, like, how is it producing, I guess, 0 for this? Because the cast B value has to be producing basically just the center point again. That's the only way we could see what we're seeing, I think. But let's find out. All right, so here is us running in debug mode now. I didn't do anything. We're still in the exact same position. So what I want to do here is just say, like, let's take a look at that specific case. So if I jump back down here, I want to know, like, first of all, what are those values? So if we do this, if I break on there, so now what I should see is this cast comes back with something like a 0 or maybe an invalid value, I don't know. Oops. So basically this cast is coming back as I didn't see anything at all, right? So I guess maybe that's the problem, is the float max is just overloading us. That makes some sense. So let's change that. If we didn't hit, then let's change that cast P to something sane. So let's do it this way. v3 cast P equals get component. Let's do it like that. If you didn't hit anything, then we know the cast P is invalid. So what we're really going to want to do is just do light distance, right? So we're going to want to do light distance times light normal. So that was probably the problem, is I was letting those float maxes flow through there. And once you let a float max flow through there, for the debug case, anything goes really. All right, so now let's try drawing it. And I don't actually see anything. So still not great. Oh. Of course, we actually have to use it. All right. So now we at least see the line, and that line is what we would expect, right? You can see that it's wrong. So if you look, it's passing through this cube very clearly. And so we can actually start our debugging process right now, because now we also have a case that is erroneously being flagged as unoccluded, but it definitely is occluded. So if we pass is test case here, right, we should now see like what this thing tested. And it descended down, I guess, into the purple region, but it didn't actually ever record any testing against this box at all, right? It didn't traverse this box in any way. And so something is up here, because when it traversed into this box, it should have, you would think, tested the children. But it didn't test the children. and I'm not clear why. I'm not clear who actually caused that to happen. If I go to the Raycast code, we're drawing the box in all cases, correct? Yeah. So we're drawing all boxes that we consider, and at some point we should have traversed down a box and didn't, right? Like, for whatever reason, this stuff didn't actually occur. Now, if we were to force it through this path, right? So if we were to do this, and now we will see all boxes that are in the system, I think, right? Or we should. There you go. I'm not sure why that's taking so long. Probably just because there's too many debug lines, I guess. I'm not sure why. Not sure why this is so slow right now. Should probably take a look at the profile. But like, look, that's very, very slow, but I don't actually know why. I guess because there's too many debug lines in the system there. But if you look at what's happening, you can see that when we forced it to consider all boxes, it did correctly intersect with this dude. So there's something wrong with the way we're checking those boxes. Maybe that new test that I added isn't actually good, right? And so let's try to figure that out, right? So if in here I said, you know, restore the test, if I got rid of this, any closer version, so that's if any of the mass values were true there, right? Maybe that was stupid, and maybe that's not actually true. So if we actually do get rid of that, let's just see, and then we can debug that tomorrow if that turns out to be our problem. So now if we let the bounding volume hierarchy do what it wants to do, the question is, do we hit it? And the answer is no. So we still don't. So is it the inside clause, or is it the close enough clause? Let's find out. I'm going to go ahead and nerf this. And so it looks like it literally, like, because that's still not recording that hit. It looks like it's literally the inside clause that's our problem. I mean, maybe. So you can see here that this means that the Tmax value has to be in front of us, which seems okay. And if the Tmin value is also behind us, I mean, that seems like a correct case to me. I mean, I guess I can't say, could they be inverted? I don't think they could be, right? But it does look like that any inside is not right. And that's basically saying, look, if Tmin is less than Tmax, which I don't even know why we're testing, because it has to be. I mean, it could be equal to, but that's the only way, right? So if the Tmin is greater than it's in front of us, oh, sorry, never mind. It's just Tmax and this. So that I don't even know why we have this test. That's weird. Just gonna note that. So if we look here, and I guess I don't know if max pass is failing. I don't know which one it is, but I can use the color value to figure that out, I suppose. Or you know what I could do is just this. to see if max pass is failing or if the other thing is failing. Although I guess no, I wouldn't, because it'll fail out on the next one. So I guess I'm not sure, right? I don't know whether the tmin is the problem here or the tmax is the problem, but somebody is the problem because somehow we're not producing a t inside value that we should be, right? Actually, I guess that's not true, because since this is an and here, we would actually need this to be that close enough case. So that's actually not true either. It could be that this is okay if there's a child count and we're inside it or we're close enough to it, right? We'll try it this way. So I don't know. So it seems like there's something busted about the way we're traversing there, but I'm not sure what it is. And if we just don't, I don't know that the t inside value is probably what it is, because, I mean, I guess that might be though, because if you look at where this thing is, of course it is right on the boundary. I wonder if it's a question of like that tolerance value isn't good enough. I mean, I wonder if this is necessary. Apparently it was. So the problem there, I guess, is we were right on the boundary of the bounding box. Right? Let me go ahead and put this in here. So now, looking at that, I mean, I guess that makes some sense why all of these were a little bit weird. Let's go ahead and go back to our normal case, because I think we're getting somewhere here. We've gotten a few things out now, and we're getting closer. So what I'd like to do is, yeah, just want to kind of change that back to this one. Oops, this one, and we'll pass false here. And I just want to look now to see what does our new pencil look like, basically. Does it look any more sane? So at least now, right, so fixing the float max bug there, at least we now see stuff somewhat properly. A lot of these look like they're hitting where they should. A lot of these look like it as well. So I'm going to say maybe we've debugged that at least to a certain extent now, right? So that looks a little more sane to me. So I'm going to go ahead now and say, all right, let's like kind of get rid of the test drawing temporarily. So I'm going to introduce yet another one here. Where I just turn it off. And then what I want to do is I want to actually just run this thing and see what it actually looks like. So we'll go to the ZBias program and we'll leave the lighting on. And then I guess we'll call it a day. And tomorrow we can sort of dive a little deeper into that stuff and see and see, if we've roughly got it working, and in which case we can move to casting from reasonable locations, which will make things work a lot better, and then go from there. So looking at like what's happening here, right? I don't really know if there's a lot of ways to interpret what we're seeing at the moment, because again, since we're casting from really erroneous locations, I would say this could actually be non-buggy. It's really hard to say now, right? Because what you're seeing effectively is just like, well, you're casting from places that are kind of right along the edges of these cubes and various stuff like that, which could just be wrong. So I think the only way to really go forward from here is now to cast from actual valid locations and see what happens there, which will be sort of the next step. And basically what we want to do, right, is we want to cast from these light probe points. But we've definitely fixed a bunch of stuff in the casting, so we probably will need to do a little more fixing. We've got a good way to debug it now. We can just kind of turn that on and off and see what's up, right? So that seems good. If we're in here, I wonder, can I now do, is there any way I can do a reasonable test cast thing where I just do this? Yeah. So looking at that, of course, it has the problem where the hot region is over here, so depending on where the hero is, I kind of have to hop into the hot, because the hot region is the only thing that's actually drawing its debug lines, right? And so if you look at what we're seeing here, it looks to me like, again, just the fact that there's stuff under the floor that's setting to 0 means you're going to get these patterns here. So I think the first thing we're going to have to do is just actually... We're going to have to actually cast from these before we can really get a better read on whether we've still got bugs in there. I mean, we probably do, but I mean, it's not possible to call from this. So I think that's the next step, and we can do that tomorrow. And then we'll have some idea of where we're at. I'm going to go to brief Q&A now. But I think we've more or less gotten out of the weeds on that. Where did you learn programming like this lighting stuff previously? Oh, I mean, I guess I'm not sure how to answer that exactly. I mean, I've been programming, what is effectively game engine code. I mean, the first thing I made was a game in BASIC, and that was when I was 7. So I mean, I've been programming this stuff for 36 years or something like that. And so, so many things you pick up along the way kind of slowly. This lighting is just an example of some stuff we're trying. I mean, this isn't a known lighting algorithm that we're using. We're kind of rolling our own because that was something that I wanted to show how to do on stream, But, all of the pieces are picked up from places. Raycasting is something that you learn to do pretty much anytime you start doing graphics drawing. You're going to encounter raycasting because it's a fundamental building block of anything that's a 3D or even 2D oftentimes game. you need to be able to know, can one point see another point? Or, alternately stated, will a projectile, like, going from one place to another, encounter an obstacle? It's just a fundamental thing you do. And so, raycasting you're going to learn to do early on. That's just something you're going to encounter no matter what you're programming in games. And then lighting is sort of like, well, if you've worked on graphics, you're going to encounter that, because you will have, lighting is a fundamental issue in producing imagery. Even if you're not doing realistic lighting, you're doing fake, something fake with lighting usually. And so, just years and years of working with this stuff, I pick up all kinds of stuff. And then when I go to implement something, I'm like, all right, here's my rough approach I decided I wanted to try this time. I wanted something relatively straightforward for Handmade Hero, so not too complicated, but I wanted something complicated enough that we would struggle with it and have to try out some things, do some experiments, make some decisions, right? Like, I wanted it to be real and something that would show up in a professional level product, right? And so I'm just kind of like navigating it with that in mind, like something good enough that we like the look of it and that it was relatively tricky to implement, so you get to see me do it, but not so ridiculous that it takes us, 1,000 hours just to do the lighting or something. And that's just because of the limitations of streaming everything means that, you kind of have a limit on how much experimentation and development and analysis you can do, right? Which parts of the CRT do you think are the most poorly designed or unnecessary, and what do you feel is missing? Well, I mean, the CRT, what do you mean by that? Do you just mean the basic C runtime library, like not like STD and stuff like that? I mean, I would say the C standard library, like the basic C standard library, like fprintf and sine and cosine and stuff. I would say, I'm not going to fault them for being poorly designed because they're so old. I think none of the C library really makes any sense in a modern context. Computers, just the basic things you're going to want to do have nothing to do with what you see in the C runtime library. So, if I was designing a runtime library for today, none of the C APIs would be in there. They're all wrong. First of all, they're all synchronous by default. Second of all, they're all based on synchronous single-threaded execution models. Third of all, they're based on text data. And, none of that's true, right? I mean, how many people have errors in their programs because the default way to open a file in the C runtime library is ASCII with translation of line endings, right? So, there's a lot of stuff it's clear, like Unix command line utility was kind of the mental model of like what people would be doing with this library, right? And that's just not realistic. Like, no one's writing that anymore. That's like not an interesting case. We're writing this heavily threaded, heavily SIMD, heavily asynchronous. Like, the modern stuff we do it just doesn't map to that. So I would say like none of the CRT is appropriate for today's programming, but that's not because the authors were stupid. That's because they were designing a library for a different time, right? Did you learn new things about game programming while working on Handmade Hero? If yes, what? Sure. I mean, the way we're doing lighting interpolation is something we made up just recently. So, anytime you program, if you program seriously, if you're taking it seriously, you should learn something. If you don't learn anything, even though Handmade Hero, I mean, I don't know how many hours, it's been maybe like 1,000 total hours or something. I don't know how long we spent on Handmade Hero, but it's a small number of hours. 1,000 hours is not many hours of programming, but it's enough. And anytime you spend that many hours programming, if you're doing it seriously, you should learn something. I mean, if I didn't learn anything from 1,000 hours of programming, boy, that would have been a real bummer. So we've definitely learned some things along the way. Have I learned as much as I normally would learn in 1,000 hours? No. And that's because a lot of the things I'm doing are like educational things. And so a lot of the time I'm spending is not necessarily doing things that are new or interesting to me. It's doing things that kind of just have to be done as part of a game engine, and I'm going to explain how they're done, rather than just grabbing some code I already have to do that and using it, right? But, you know, even in an educational stream like that, 1,000 hours is plenty of time to come upon some new things, and we definitely have. Can you imagine any debug tools that would make stuff like graphics programming and lighting easier to debug, especially for beginners? Actually, I think you don't even really need to think about beginners. You've watched me try to debug the lighting today, and what was I doing the entire time? I was like adding debug code to like draw stuff, right? I had to make that debug line system. And without it, we would have had no idea what the heck was going on, right? Modern debuggers don't give you any ability to do any of that stuff. If you took a debugger and you added the ability to insert this kind of code, so like if I could go in my debugger and add this as markup in my code in the debugger anytime I wanted to, right? That would be so cool, because then all of this crap goes away and the debugger could have all kinds of tools for like spinning around and rotating and stepping through and watching the lines draw, right? I mean, it would be friggin' awesome, right? And there's no reason not to do it. It's just, I mean, nobody writes debuggers anymore. And Remedy BG, which is the one I use on stream now, was something that a person did in their spare time just so we wouldn't have to suffer with Visual Studio, right? I mean, Visual Studio is the thing that people use to debug. It's one of the only debuggers that exists on Windows that anyone even uses. There's WinDBG and Visual Studio, and they're terrible. They don't have any features for actually debugging code, right? All they can do is display a watch window poorly. You know, and Remedy BG is much better, right? But it hasn't had, I mean, it's a part-time project. It hasn't had years of development that it would take to put in all kinds of really good stuff like viewing images and showing transforms on them and showing 3D graphics and rotating around it and augmenting your code with 3D graphics drawing and explaining what space things were in. And like, you know, I mean, that's a ton of work, right? And that's exactly what Microsoft should have been doing. But, you know, they're just, I mean, the Visual Studio team isn't good. They have different priorities. They don't know any of this stuff. They probably don't even know how to draw 3D graphics, let alone what you would actually need and implement it. I mean, they can't even do basic stuff like have the watch window update in a reasonable amount of time, right? So forget it. Like, you're not going to get any of those advanced features. And they're too busy doing stuff like, oh, I needed to make some kind of weird integration with Trello or something, right? Like, that's what they spend their time doing, stuff that's totally useless for actually debugging code, right? Now, I'm hopeful in the future, you know, Remedy BG is a great addition to the debug arsenal. It means now you get Visual Studio's features without having to install Visual Studio, and they run quickly and cleanly. That is a huge improvement. I know Alan Webster, the guy who wrote 4Coder, and Nick Slivka, the guy who wrote CDBG, are now at RAD, and they're doing a debugger, and it's supposedly coming around pretty well. So I think we will get improvements, but basically, it took the programming community going, this is absurd, these tools are garbage, and a few years ago, right, and starting again to get those projects going. And until they come to fruition, we're going to be stuck with none of this, right? And so it's only through the efforts of people like George, who wrote Remedy BG, and the guys at RAD, and who knows who else, right? It's only through their efforts that we're ever going to get out of this pit, because the professional, quote-unquote, development tools, JetBrains and Visual Studio Code and Visual Studio, they're just garbage. They're not made for real programming. They're made for this kind of like modern toy programming where people just jam libraries together and cross their fingers and everything sucks, right? And so it's going to take like some real effort to make hardcore debugging tools again and to get some projects alive. It's hard because the number of people who want to buy a fluffy crap debugger or just download one for free because they're used to not paying for software, like is the case in like web development, right? That doesn't provide funding. right? You need some way to provide funding to good programmers to make good debuggers, and really big 2 thumbs up to Rad for actually funding that project, right? Because without them, we'd probably never get there. And you know, in an ideal world, enough people would have bought Remedy BG to give George the funding he needs to go full time, but that hasn't happened. And so, you know, I don't know what to say. We're in a bad situation. Is it possible to get cl.exe and MS Build without installing Visual Studio? I don't know about MS Build, because I'm not familiar with that. But cl.exe comes with the SDK development tools, or used to anyway. So I would say yes, you can. How do you split your time between learning theory and practice? I don't really know how to answer that question. They're sort of the same thing. Like when you're programming, you're usually also having to learn theoretical things if it's in an area you're not sure about. And you have to kind of read papers periodically and continuously to kind of keep up to date. So I don't really think of my time as being split. I think of that as just sort of integrated in, right? How many hours do you expect Handmade Hero was going to be at the start? I don't know. I said I would do 600 episodes. And we'll probably take more time than that because when we finish the lighting, we will have what I would consider a fairly complete engine, right? So, you know, you can hop around the world, you can put enemies in it, it's got full lighting, it's got assets and texturing and all that good stuff, and you can reload the textures and you can reload things and you can put new assets into it and do all the things you would normally do with an engine, right? But we're going to want to build some gameplay and then test it out and maybe tweak the engine based on what we build for gameplay and, you know, put together a real game that, you know, probably won't be the world's greatest game or anything because I'm not a game designer. But, you know, we should do enough to satisfy ourselves that it was good quality code, right? And that everything was working well. And so that'll probably take a while. So it looks like we'll maybe do 600 episodes on making the engine and a basic game, right? But then, you know, however many episodes we want to spend beyond that to make as much game as I feel like making, I couldn't tell you. And I'm not sure I care. Like, I'm not sure I care how many episodes it takes. I'm pretty happy with, like, I think we did a really good job, actually, building an engine on stream. It's a very complete engine, has a lot of stuff it can do. And it's much better than what I was planning to make. I was planning to make just a simple 2D engine, but this is like a full 3D engine with fake perspective things and real lighting and, like, you know, a lot of stuff that was kind of better. Are you planning to do another series? No. Any plans for physics? Not beyond just the basic special effects stuff. Like, we already kind of have some stuff in there for particles, which is basic physics stuff. But we wouldn't really be doing anything beyond that kind of stuff, I don't think. All right, let's go ahead and wrap it up. All right. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org. And it comes with the source code so you can follow along and do your own experiments. I don't necessarily know if doing the light casting for light probes is a good exercise for folks who want to follow along at home. Might be a little bit much to do over the evening. But that's what I'll be doing tomorrow, so tune in for that and we'll get that going. That will put us in a position to actually be computing shadow rays from realistic locations in the scene and spreading that light data back out to the voxel, which is what we want to do. You probably don't want to try that as an exercise, so skip that. But I'll be back to start that, and then once we get there, then we'll be in a position to start turning the crank on the lighting. Because that'll be basically when we can start to go, okay, let's first of all debug any raycasting bugs that we still have in there, make sure that works okay. Then move up to like, okay, now let's actually convect the light around. So we'll get our secondary, secondary, tertiary, quaternary bounces, so that more like light motion. And that will finally give us a way to play with the lighting and the lighting voxel interpolation fully, and we can tackle kind of what I think is probably the last remaining problem we have, which is when we have a bunch of lighting information coming in now, how do we map that down to a 4-iterator system? Or, do we want to change that 4-iterator system a little bit? I don't know. So I don't know exactly what we want to do there. And that's going to be the last kind of big unknown for us that we got to start playing with. How do we do that down project? That's it for today. I'll be back here tomorrow, same time, same channel. Till then, have fun programming, everyone. And I'll see you on the internet. Take it easy, everybody.